Chen, thanks a lot for coming, and he will present about dark matter, WIMPs, FIMPs, and
Thank you for inviting me to talk. I will speak in English because my Spanish is terrible. But yeah, today I will talk about dark matter, and I'm going to talk about the three of the many kinds of dark matter that there are, or that we think could exist consistently. WIMPs, which is the standard in the community for the last 3 or 4 decades, you probably have heard of, but I remind you about it. I'll then contrast with FIMPs, which is another kind of particle dark matter. But before talking about particle dark matter, I'm going to talk about this idea of primordial black holes, which is a very different kind of dark matter because these are macroscopic objects. And then, in the second part of my talk, I'm going to ask the question, what if these coexisted? And is there any interesting physics which arises, or new constraints which arise in a universe which has both primordial black holes and particle dark matter? So first, I'd like to say this is I've been a long time visitor to La Plata, but my first time talking in the astrophysics department. Oh, how do I change slide? My father-in-law is, of course, as many of you know, Fidel who was a professor in physics for many years. We were very saddened when he died. He was a great mentor. This is him with my son, when my son was 2. And so, yes, I was very sad to see him pass. We actually wrote a paper, which I won't talk about today, which we dedicated to him, just to say that, we are very saddened. But we will continue to come back to La Plata. My wife's family is still here, so, we remain strong connections. Okay, so the talk today, as I said, we're going to first talk about primordial black holes. There's an interesting idea that we may have seen some hints of primordial black holes in the data, which I'll talk about, but they're very tentative, but also very fun. Then I'll switch and talk about candidates for particle dark matter before going on to talk about combinations of the two. I'm going to assume that you know what dark matter is, but let me just say in a sentence, in case it's not something you think about. Dark matter is this idea that when we look at the predicted motions of astrophysical bodies throughout the universe at different length scales and different time periods, they seem to behave as if there's more matter than we can observe within baryons alone. So the classic examples of these things are like rotation curves, where we look at how fast objects move around the galaxy. And if you were to look at how fast the objects on the exterior of the galaxy are moving under just the gravity of the stars, you get a mismatch between Newtonian physics and observation. Normally requiring you add either new particles which only interact with gravity and don't interact very strongly with the known particles, or you change the laws of gravity. And changing the laws of gravity is very hard. So accepting that dark matter is a phenomenon which exists, I'm going to spend today talking about ways of explaining it. So the first idea was to introduce something called a matcher. It's a massive compact halo object. Originally, these things could be thought to be perhaps failed stars or rogue planets, or potentially small black holes which don't have their origin in stellar collapse. These are a natural dark matter candidate because they are very hard to see, and so can describe it. Primordial black holes are perhaps the most quintessential example of this. And importantly, we know that black holes exist. We know that black holes exist from observations made by the LIGO Observatory, which have given fairly conclusive evidence that what we are seeing is black hole mergers. But an important thing about black holes that LIGO has observed is that this is the mass of the black hole, and the x-axis means nothing. You can see that you have 2 of these blue dots, and they lead to a third blue dot. This is a one-merger event, okay, with this being the resulting object. So you can see we're actually starting to map the mass distribution of black holes in the universe. But you may note that this is not a plot which goes, well, the axes don't go infinitely high and infinitely low. And an interesting point here is that all of our black holes that we've observed, they begin with something of order a stellar mass. The reason for that is because astrophysical black holes, as they're known, they arise from the death of a star. And because of that, their mass, the minimum mass which they have, is tied to stellar physics. And so it's well known that you simply cannot produce astrophysical black holes which are lighter than stellar mass. However, it was seen by Hawking and separately by Zeldovich and Novikov that there was another way of producing black holes, and these were in the early universe. Potentially, after the period of cosmic inflation, all of your energy density is, at least in the conventional theory, is stored in the inflaton, and you need to somehow move that energy density from the inflaton back into the standard model degrees of freedom. Now, we know that to reproduce standard cosmology, when that reheating event occurs, that your energy density should be fairly uniformly distributed. Otherwise you run into problems with matching to cosmological observables. However, it is allowable to have an almost uniform distribution with certain density spikes. And these density spikes could quickly collapse to form black holes, potentially. Or potentially collapse slightly later in time if, for instance, there's some supporting pressure and then a phase transition removes that pressure and then these objects collapse. So this is a way of generating black holes without reference to stellar physics, and as such, the mass of these black holes is no longer tied to, this is what's called the solar mass, this is the mass of the sun. So these primordial black holes can have arbitrarily large range of masses, up to them being constrained by experimental observations. And of course, black holes are very dark. They interact very little with standard model particles, apart from perhaps acceleration or accretion dynamics, which can lead to observable signals, and gravitationally. As such, they are an ideal dark matter candidate, but you can try to constrain their existence. So one of the main ways that we look to constrain these, what are called the more general massive compact halo object, or MACHO, is through what's called a microlensing search, which I'm sure many of you are familiar with. The idea is that when a massive body passes between the Earth and some source, and naively you would expect the source to block that light from the star. But according to general relativity, the heavy source causes a bending of the light, and that actually results in a brightening of the source. Such a microlensing event is indicative of a massive object passing through the domain of your telescope. As such, if you think you have a population of the large dark objects, such as primordial black holes, if you know how many there should be, and in particular, we know how much dark matter that is, there should be 5 times as much dark matter as there is baryonic matter. So for a given dark matter, for a given mass of your primordial black hole, there are so many of these objects, and therefore you should be able to predict the number of microlensing events you get. And so people have gone about trying to plot these constraints. The microlensing constraints that I just described are what form this blue exclusion band. There are various other limits from cosmology, and they largely come from things like CMB distortions. And there's also this limit here, which is called evaporation, which I'll talk about in a moment. So it's worth looking at the axis of this. So on the y-axis, this is called the fractional abundance of primordial black holes. So the question is, if primordial black holes exist, do they need to account for all of the observed or the inferred dark matter? Okay, so it could be, if you lie on this top line, then your primordial black holes are your dark matter. That's all of it. However, if you lie at 10⁻⁻⁻⁻, then this is 10% of your dark matter is in primordial black holes, and 90% of your dark matter is elsewhere. So, and then on the x-axis is the mass of your primordial black holes. And I'm going to assume they all have a uniform mass due to them being formed by a process at some given energy scale. So this is in units of solar. It's actually kind of useful to think about it in terms of what actually this means. So of course, 10 to the 0 is the mass of the sun, and then there's Jupiter. Pluto is at 10 to the -9. This gap, you'll see here, there's a gap here in the exclusion plot between the limits from microlensing and evaporation. This is what's called the asteroid window. The idea here is that if you had a population of asteroid mass primordial black holes, which were all of the dark matter of the universe, then at the moment that is completely consistent with data. And down here, in lighter objects of all of the 10 to the -18, that's times the mass of the sun. That's around the mass of Halley's Comet. So very small astrophysical objects. Now this band here is called the evaporation limit. The idea is that due to Hawking, black holes, while black holes are classically stable, quantum mechanically, they do actually lose energy through what's called Hawking radiation process. And this would actually cause smaller black holes of order Halley's Comet or less to evaporate to such a degree that they either do not exist today because they have evaporated all of their mass away, or they're currently evaporating at such a rate that they would be observed in indirect detection type experiments. So they're observed in X-rays and things like this. This leaves this nice mass window here, where these primordial black holes will be 100% of the dark matter. And it's also worth considering scenarios where they're perhaps 10% or 1% of the dark matter. So as far as primordial black holes go, these are really the most interesting areas because, of course, there could only be a small number of these in the entire universe, but then they'd be very difficult to find. But even if there exists a sizable population, then this can potentially have an impact on astrophysical observables, as we'll talk about later. What's very exciting is that over the next, say, 5 to 10 years, these limits are going to get substantially stronger. So there's a set of new experiments coming online, MEV gamma ray telescopes, there's the Roman microlensing experiments, and the Rubin microlensing experiments, and these are going to strengthen these bounds. The current bounds are shown in the blue microlensing bounds I showed you just was this blue region, and you can see that this is going to increase. This was the asteroid mass gap, and you can see that a lot of this mass gap is going to get closed in. So a lot of the interesting areas that I showed on the previous plot are going to be either constrained, or you will potentially get a discovery, which is very exciting. However, there is actually one hint. Already these microlensing experiments have been going on for a couple of decades. There's actually one hint of primordial black holes in the data. This is due to what's called the Oval telescope. And they did precisely this microlensing experiments search, and they found more microlensing events than expected. So when these experiments place these limits, it's not that they are background free. There do exist things like brown dwarfs and rogue planets, which will show up as microlensing events. However, what you look for is an excess above the population of these events that you expect. And that's precisely what Ogle discovered in their observations, and they set, or they identified there was a particular excess in this region here, which corresponds to a mass of around half an Earth mass to 20 Earth masses, and which would have to account for, this is 90% or 0.5% of the dark matter. So this is interesting. It's interesting for two reasons. One of those reasons is that this is actually very consistent, that you could have such a, this is a sizable subfraction of the dark matter could be in primordial black holes. It also tells you that most of the dark matter is not in primordial black holes. It must be in something else, potentially in particles. Okay, some new, beyond the standard model particle, like a WIMP, the classic weakly interacting massive particle. The other thing which makes this interesting is this is a region which is going to be tested in the future experiment, so it'll either be verified or refuted. However, there's another interesting anomaly, observational anomaly with exactly the same mass range. Right, so this is the mass range of about 1 to 10 or 1 to 20 Earth masses. And this actually comes from an unexplained dynamics within our solar system. So the unexplained dynamics which have been seen is that if you look at objects past Neptune, these are what's called trans-Neptunian objects, very creatively, you find that they have a number of behaviors that are very counterintuitive. In fact, it's notable that all of the dynamics within Neptune are well understood by astrophysicists as well. These are solar system physicists or solar system, including people like Batygin and Brown, who discovered all the dwarf planets. But when they look out at objects past Neptune, they see a number of strange phenomena. The first of them being there's a lot of high inclination objects. So objects in the solar system largely lie in a plane, which being the plane of the planets. And this is well understood. Why that happens? I mean, this is simply just a reduction. It's a combination of a loss of energy, which collapses things to the plane by radiating off energy via a photon. But also, if you have objects outside the plane, then eventually they get dragged down by frictional interferences, and the gravitational attraction of the plane should bring things into the plane. So if you have a large number of bodies outside the plane and which just stay outside the plane, this is actually quite surprising. The other observation that people have made of these trans-Neptunian objects is they seem to cluster in one part of the sky. Typically expect bodies in any system to be somewhat uniformly distributed, unless there's some reason for them not to be. But when people went to look at the distribution of the orbits, so this is showing you the orbital parameters of different small planetesimals, they found that a lot of these, in particular subclasses, a lot of these were in one part of the sky, with very few of them in the other part of the sky. And this asymmetry in the solar system is not really understood. It's not understood, firstly, why it would arise, and secondly, if there was a reason for it to arise, it shouldn't be stable under time evolution. You would actually expect these orbits to precess and eventually become uniformly distributed. So, after observing these things, the astronomers had a simple but elegant solution to this. They proposed that perhaps there is a new planet. This is actually very similar to how Neptune was discovered. People looked at the orbit of Uranus, and they found that the orbit was slightly different to Newtonian predictions, and they predicted the existence of Neptune, and then they went and observed it. So now they have a set of gravitational anomalies in our solar system, and they essentially hypothesize that perhaps there is a new planet in the outer solar system which is causing these gravitational anomalies. Planets in the outer solar system are very hard to see because the main way you look for them is in reflected sunlight, and the reflected sunlight would be dim because they're far away. So they ran a bunch of Monte Carlos to try and work out what sort of properties a new planet would need to be able to explain a number of these gravitational anomalies simultaneously. And they came to the solution. There's a sort of a range of different possibilities. You run a big Monte Carlo to see what works. But they found that if you had a new gravitational source in the outer solar system, which had a mass of about 5 to 10 Earth masses, and it was about 450 to maybe 1,000 AU away from the sun. Now, for reference, 1 AU is the distance from Earth to the sun, and 50 AU is the distance from Pluto to the sun. So these objects are 10 to 20 times the distance of Pluto to the sun. They would be somewhat eccentric in that orbit, so more like this than circular, and they would have some modest inclination. If you had such a planet in your solar system, or gravitational source, let's say, then you can explain all of these strange anomalies in the solar system, which is interesting. It's interesting because it's very testable. However, me and my collaborators came and asked, does this need to be a planet? In particular, we already knew about the oval observation that said that there was potentially a population of primordial black holes in exactly the same mass range. Is it plausible that you could put a black hole in the solar system, a small one, sort of an Earth mass black hole, and reproduce this without running into contradiction and being at least as plausible? Well, the answer, gravitationally, the answer is yes. You can do since it's all gravitational physics, it does not care if it is a planet or a black hole or anything else, as long as it sources the mass. However, you would look for this object in a different way. You look for planets with reflected light. How do you look for a black hole? It's complicated, it's difficult. But there's already a hint here that you know that this black hole is maybe only 90% if you believe the oval observation, as well as is related to this. You know that 90% of the dark matter or more must be in dark matter particles. And these dark matter particles will probably cluster around the black hole. And when you have a high density of dark matter particles, they will tend to annihilate. And those annihilation signals can be observable. And in particular, we did some back-of-the-envelope calculations, and we showed that if you make this a conventional WIMP particle, which comprises the 90% of dark matter, then you find that this is actually extremely excluded. A black hole in our solar system surrounded by these WIMP particles, which I'll talk about what they are more shortly, would be brighter than the sun. But if we went to different types of particle dark matter, and I'll say what this is shortly, such as the FIMPs, then these are to the idea that you put them in a future experiment, but they're not currently excluded. But this is largely what got me thinking about combinations, this observation in particular, the oval observation, combinations of particle dark matter and primordial black holes. So in the latter half of this talk, after I've introduced what the WIMP and the FIMP are, I'm going to tell you why these limits, particularly limits in gamma rays, become so strong. Okay, so that's all what I'm going to say about primordial black holes for now. Any questions? Drink some coffee. Yes.
These beams has diffraction certainly weaker than weak.
Let me get to that. That's my next.
But no, like the question would be some other kind of particles, external neutrinos, also typically have interaction like so-called super weak.
You would have to go and yeah, you have to go and calculate it. But so let me tell you how you do that. Let me tell you what how to calculate the limits, and then you can do that. It's a perfectly good idea. All right, so I'm going to introduce the particle dark matter. We talk now about primordial black holes. They're an excellent candidate, but they are microscopic, meaning you can perform these microlensing searches. Particle dark matter, you can't perform microlensing because they are particles. And they come in a large number of varieties. So I'm going to talk about weakly interacting massive particles, which are the classic scenario that people have thought about for 40 years. And I'm going to talk about feebly interacting massive particles, which are interact much weaker with the standard model. And because of that, they need different searches. Yeah, question.
You expect these particles from the black holes?
Yes. Yeah, okay. So what happens, and I'll talk about this more in a moment, is that these primordial black holes, they, especially in the WIMP case, they form very early in cosmology, potentially immediately after all of the thermal bath of the universe is populated. At that time, there is a thermal bath of dark matter around it, and the dark matter is free streaming, so it's relativistic. At some point, the dark matter stops being relativistic and becomes non-relativistic, and at that time, the black hole is a gravitational source that captures a volume of dark matter within its gravitational influence. And then subsequently, that dark matter undergoes gravitational collapse and forms some sort of density profile around it, which I'll show shortly, although I won't do the maths. So what happens is that you form dark matter structures around this primordial black hole, much like the galaxies have dark matter structures, but they're much denser than you would typically expect from astrophysical black holes.
And they last.
They last. They don't last in an unchanging way, but yeah. So dark matter in principle shouldn't decay.
They also don't get swallowed by them.
Yeah, so the only way that the black hole swallows is if it physically touches, right? So I'm assuming that they're not charged. The black holes aren't charged because that's a typical assumption. In particular, they're not charged under any force that dark matter is. And so the only way that it gets swallowed is that the black hole hits one of these objects. The geometric cross-section for the black hole is small because a lighter black hole will be relatively small. So an Earth mass black hole is around the size of a tennis ball, and the dark matter halo that gets formed is maybe 100 AU, so the size of a solar system. And so although they may swallow a small number, it's a negligible amount. So yeah, but it's a good question. Okay, so I'm going to talk first about, I'm going to introduce these two classes of dark matter models, dark matter particle models, and then we're going to look at the interaction between these and primordial black holes. So in the classic idea of WIMPs, it starts with the very elegant initial condition that says the dark matter is in thermal equilibrium with the photons and with the standard model thermal bath. That means that the number density is comparable. If you have an over-density in dark matter, then it will quickly annihilate back down to its equilibrium density. If you have an under-density in dark matter, it will quickly be repopulated to this equilibrium density. Because of that, the initial conditions are essentially agnostic. It doesn't matter if you change, because it's in thermal equilibrium, you could initially have any excess or deficit of dark matter, and it would come back into equilibrium, and you have this sort of beautiful initial condition, which is agnostic to anything early. So I'm going to plot this in terms of what we often call the yield, which is the number density over the entropy density. And this is my time axis, which is the mass divided by the. And so what happens is, as the universe expands, the temperature drops. And these objects, they stay, because they are in equilibrium, this yield stays at some constant value, and this continues until you hit some critical threshold, being the dark matter mass. When you hit the dark matter mass, then when the temperature of the dark matter mass, I should say, then there's not enough kinetic energy in the thermal bath of particles to be able to produce dark matter particles, so this process switches off. But two dark matter particles can still meet each other and annihilate into standard model particles, because typically we assume that dark matter is relatively heavy, heavier than at least some standard model particles. So annihilations continue, production ceases, and you get an exponential suppression in the number density of dark matter. And this continues until a given dark matter particle simply cannot find a pair to annihilate against, at which point these processes switch off. Okay, and so you get an exponential suppression in the final abundance of dark matter, which only depends very weakly on things like masses and couplings. Now, the thing that made this scenario very beautiful is that some prediction for the final abundance of dark matter, and if you take that prediction and you put in a good guess for the mass and cross-section, annihilation cross-section of dark matter, it gives you exactly the abundance we see today. And this is one of three things which makes this attractive. The three things that makes this scenario attractive are the fact that it has this agnostic initial condition. It actually turns out to be incredibly easy to build experiments to search for. And if you put in good guesses for what you think the dark matter could be in terms of its mass, you get the right answer. So those good guesses are, we think something special might happen at the electron weak scale, or just above, right? This is connected to things like the electroweak clarity problem, or maybe you want to understand the structure of the standard model. You would like to say maybe there's new physics just above the standard model, which gives you a math scale for where you think new physics should enter. And dark matter is definitely new physics, so let's link those things. So if you take the dark matter mass to be of order the electroweak scale, and you take the cross-section to be of order the squared Fermi constant, so that's of order, say, the z mass to the 4 in the denominator, then what you find is that this gives you exactly the right amount of dark matter today as you need to explain observations. This is what people call the WIMP mirror. Now, this is beautiful, especially so because it's testable. Looking for objects which are 100 times the mass of the proton turns out to be very nice because you can hope for these objects to collide with a proton, particularly because you know there should be many of them. To reproduce the amount of dark matter we see in the universe, it means that these should be 100 GeV particles need to be incredibly abundant in our galaxy and even in our like galactic neighborhood. And so you can look for these in a number of different experiments. Oh, my PDF conversion messed this up. Let me go. Oh, is it better? So you can look for this in a number of different processes. The first process you could have to look for is dark matter particle meets another dark matter particle and annihilates to 2 particles in the double back. Let's write that as these. So that is reading this Feynman diagram, this toy Feynman diagram. Now we know that this process should happen because we assume that dark matter is in equilibrium in the early universe, so it should be able to annihilate. We also know that you could read this backwards, and reading this backwards means that dark matter should be produced by this dipole. We know that this should happen because it was in early equilibrium. And the third way to do this is by scattering. There is a sort of scattering cross section.
So this is annihilation, and this is reduction. So when looking at this diagram, we see there are 3 different ways to search for such an object. The first is you could look for residual annihilations, although in the majority of the universe, these annihilations have switched off due to this freeze-out process. In areas of annihilations, these include places like the galactic center and galaxies, where we think densities should be much higher.
In fact, we know densities for galaxies are extremely high in dark matter because there are some dwarf galaxies which are almost 100% dark matter. You can only see them through lensing, gravitational lensing. The place you can look is collides. So you
you can have 2 particles, standard particles, which produce maybe radiant of some initial radiation, maybe an initial jet, and then produce dark matter, and that shows up as missing out the light. Just like, yeah, so it looks like the violation of energy conservation, but actually that's because you've got some dark matter in you know, making physics not break, and giving you a signal of dark matter. Again, you can place limits on just, and you can use this to constrain models. And finally, you can look for one of these scattering experiments where your dark matter comes in, interacts with something in, this is a container here,
and then you look for that scattering cross section. And so what you have to constrain is the scattering cross section as a function of dark matter mass. And this is such a good idea that people built a decade's worth of experiments starting in 2012, going down to about 2025. And so over the last decade and a half, we have actually sort of systematically gone into this cross-section mass space, aiming to get this circle here, which is our favorite theories. These are where the dark matter couples via the Z to standard model particles, couples via the Higgs to standard model particles. Maybe it's a supersymmetric neutralino, which is a classic WIMP candidate. And over that time, all of these searches have excluded all of the better part of this favorite theories area. However, there still exists some amount of area where you can get these to work, these theories, but they're sort of less elegant. The further you go down to cross-section space, the less elegant it is as a solution. Do you have a question? No, just stretching. One thing worth pointing out, this yellow region is called the neutrino floor. Now it's been rebranded as neutrino fog. If your experiment gets below this line, it's so sensitive that it can't distinguish between neutrino interactions from the sun or from the other atmosphere and dark matter interactions. So you get an irreducible background of neutrinos in your experiment, which makes it extremely hard to make progress. Okay, so this has made the fact that we built a decade's worth of dedicated machines or experiments to look for dark matter, and we failed to find it in the places we thought we would if it was a WIMP, made people try to think about other scenarios. I should say there are dozens of other scenarios. I seem to have lost a slide where I had a giant list of scenarios. You may have heard of some of these scenarios, things like axions, or, oh, there's a bunch, SIMPs, or they all have strange names. But I'm going to sketch my favorite one, which is called the FIMP, or a freezing dark matter candidate. One of the reasons I like this is because it's highly distinct from the freeze-out scenario, starting with the initial conditions. So you might recall that in the freeze-out scenario, or the WIMP scenario, you assume that the dark matter is in standard equilibrium. In the freeze-in scenario, you assume there's no dark matter initially. And instead, what happens, because there's no dark matter, there's no annihilations. What happens now is the dark matter is slowly produced through standard model bath interactions. And essentially what you're doing is you're leaking energy from a hot bath or into a cold bath. So it's simple thermodynamics, and this populates the amount of dark matter, and at no point, this is an assumption of the theory, at no point you come into thermal equilibrium, and at some point, production switches off, and you have some final abundance. Okay? So you see that it's very different physics that sets the final abundance of dark matter, and because of that, you get very different cosmological histories, and you also get very different forms for what the final abundance of dark matter is. So the Y at FIMP is effectively the final abundance of dark matter here. In one case, in the WIMP case, it goes like the inverse of the mass and the annihilation cross-section, and in the other case, it goes like linearly in the mass and the production cross-section. This is interesting because of these different parametric forms, you find that you need very different parameters to match today's observed dark matter abundance. So in the WIMP case, this works because you assume that this is very similar to the weak nuclear interactions, and so the strength you need is something like a coupling strength of 0.1. In the FIMP case, at least in the case which is sort of most similar to the standard WIMP, where you take a dark matter mass of order, say, the proton, or maybe the Higgs, then the coupling that I need must be something like 10 to the minus 9. So you can see there's sort of 8 to 9 orders of magnitude difference in the coupling strength. And because of that, most conventional, or all conventional searches for dark matter fail when looking for this FIMP dark matter candidate, apart from maybe a number of very special cases. So this is the strength of the theory, but also a weakness, right? The weakness is it's incredibly difficult to see, but the strength is it's not excluded like the majority of the WIMPs. However, it's maybe a little bit disappointing that these FIMPs are hard to see, but there is a special class of scenarios where actually they become much more easier to see. And that is when I have primordial black holes and a population of particle dark matter. So I'm going to start by just talking about the WIMP case, and then I'll move to talking about the FIMP case. So, I explained, so if I have a population of particle dark matter and primordial black holes, I define this fractional abundance that I did before. And what happens is, as I mentioned, they form a ball of dark matter around these primordial black holes. And then you can look for an annihilation signal in the dark matter, and this leads to things like positron excesses, gamma rays, they're actually observable. If you want to do this, though, the first thing you effectively want to do is you want to calculate the flux. How many of these particles come to you, and then you can compare that to your predictions or your data. Okay, and to calculate the flux, you need to know quite critically how dense the profile is around these objects. So you can go away, and I lost the original reference actually. There was a very good paper by a French group who calculated this with extreme care. And they showed that these density profiles, these have been called spike profiles in the literature because they are very, very steep relative to other astrophysical environments, and they come out looking like broken power laws. There is some sensitivity to the particular mass of the dark matter and the mass of the black hole that leads to where this power law breaks and what the powers are. But you can calculate this. So I'll refer you to our paper and references therein. And what you find is, as I say, there's some different regimes where the power law that you get either changes at different parts. So this is the radius of the black hole in Schwarzschild lengths as a function of the mass of the black hole. And you see that in some cases you get one break in the power law, in some cases you get two breaks in the power law. So you should read it this way. Each line vertically gives you one density profile. And at some point there's a terminal radius. That terminal radius is essentially the distance of the gravitational influence of the black hole at the time of decoupling of the dark matter from the thermal bath. However, there's some other physics that goes on here, which is very interesting, which is that in the central regions, you will actually get dark matter annihilations given enough time. And so instead of having all of this rich physics on the interior, you end up with profiles that look more like this, where all of the very dense regions of dark matter annihilate away, leaving you with a density core, which then slopes away to in the same profile. Interestingly, velocity-independent dark matter. So in velocity dependence, then you actually get even richer physics, which I'll talk about in a moment. But this is what the late time halo looks like, and this is what the early time halo looks like, which is an important distinction when you look at the limits. Because if you look at if you actually look for the annihilations of around these black holes in our galaxy, then you're looking at nearby objects, and these were late time. If you look for extragalactic gamma rays, so annihilations from outside our galaxy, these tend to be dominated by very, very far away objects and therefore very, very old objects of light. Our profiles more like this. In fact, you have to integrate over all of the different redshifts, accounting for how this profile changes. Final thing which happens, which is that for the galactic objects, for the galactic black holes, they will also encounter other objects. They may encounter the central black hole, they may encounter stars, and every time they come close to an object, it's objects, and so just from their gravitational interactions, much like if you consider a solar systems, when they pass nearby another star, they often strip away the exterior planets. So this is, if you account for this stripping with a Facultad calculation, you actually show that in the case where you have this central density core, very commonly this is all that remains. Okay, so if I have a density profile, and I'm going to think mainly about extragalactic gamma rays, which means I take the full spike profile and then integrate over the redshift. I want to calculate the flux of extragalactic gamma rays to me, so how many do I see? To calculate that, I need the annihilation rate, which goes like the density squared times the cross-section, and I integrate over this with the radius. And then this rate goes into my flux calculation, and so the flux that I see, or the differential flux, goes like the annihilation rate times the number of these dark matter particles, primordial black holes. The number of primordial black holes is simply related to the fractional abundance, so I know that there's some fraction of the dark matter. So that tells me how many there are. This is Hubble. This is a function which describes the opacity of space, so how easy it is for the signal to propagate to me. So at very early time, this is not 1. And then finally, I need to know about how the photons arise from the dark matter. So does a dark matter annihilation around the black hole lead to 2 photons? Does it lead to 2 pions, and then these pions shower into photons? And so this can be, in principle, this is very model dependent. And I think we assume something very simple, like each dark matter annihilation gives 2 Bs. We assume something sort of semi-realistic. We assume dark matter goes to BB bar, and then BB bar hadronize. And that gives a characteristic photon spectrum, which is well known, and you can simply just look it up. Okay? And so once I have this, once you piece this all together, then you get precisely this differential flux. This tells you how many photons you expect, and then you can actually compare this to experiment. So it turns out we know what the extragalactic flux is. The extragalactic flux has been measured by Fermi. It's all these little error bars. And you can ask, I take a particular dark matter model. So an S wave means velocity independent cross-section. I take the dark matter mass to be 1 TeV, the black hole to be about the mass of the moon. And I ask, what is the largest fractional abundance? What fraction of the dark matter can it be? Before I'm in, with the assumption that all of the extragalactic gamma rays come from annihilations around primordial black holes, when would that come into conflict with observations of Fermi? So when would I produce more extragalactic gamma rays from these black holes than Fermi observes, which is clear contradiction. And you find that this is 10 to the minus. So this is one example. You can then vary these parameters and ask, how does this constrain this fractional abundance? So this is the scenario of WIMP dark matter with primordial black holes. And so you can plot it on a similar plot as before. So before, this is if I just assume my dark matter doesn't annihilate, and I simply do searches for the primordial black holes, then I have this plot from before. This is the micro-lensing bounds. This is the evaporation limit. And now I add this new information that the dark matter can annihilate. And so this actually gives, so if I live here at this point 10 to the minus 2, that means that 99% of the dark matter is a particle. I'm going to assume it's a WIMP. I'm going to assume that WIMP has one of these masses. And so this actually tells me the exclusion bounds are much stronger. So it tells me that I cannot live here, 10 to the minus, well, let's do my next slide. I cannot live here with a mass of 1 TeV unless the amount of primordial black holes is less than 10 to the minus 7 times the dark matter abundance. So that's an extremely strong bound. Of course, we could still live here, okay? But this is ruled out by annihilations around the black hole. It's extremely nice. It's an extremely nice result because it increases the strength of these limits by 5 orders of magnitude. So this is the simplest possible case you could think of. It's this weakly interacting massive particle that which has no velocity dependence in its annihilation cross-section. There's a couple of small changes to this could actually make the physics more interesting. You could add velocity-dependent annihilations to the WIMPs, and we can also consider FIMPs. You can also consider the stellar neutrinos, or self-interacting dark matter, or axions. They're all very interesting, but we did these 2 first. Yes?
Yeah, I think kind of to say to the former statement about parametric distribution is that it's extremely normative particle model dependent, while the other constraints are just based on regular black.
Yeah, because it's model dependent. So you don't know what your dark matter particle is. So if your dark matter particle only interacts gravitationally, then these limits essentially go away. But if you think it's a classic WIMP,
Yeah, exactly.
then you're constrained. So yeah. But I think if you had simply a gravitationally interacting dark matter particle, then this would not work. But there's an interesting question. There's a question about why do we like the idea of WIMPs and FIMPs? Why do we think dark matter should be connected to the standard model? And there's a couple of things that. So firstly, in the WIMP case, you find that you naturally get the right abundance by putting in reasonable guesses for how you think it should work in the WIMP case. And that kind of is such a beautiful picture that it's hard to ignore. There's also this notion that if you look at the amount of dark matter there is and the amount of baryonic matter there is, you find that the numbers are about the same. There's 5 times as much dark matter as there are baryons, so it could be 100 times or 1,000 times, and it actually wouldn't change much of astrophysics or cosmology. It wouldn't change the chance that the galaxies had life, for instance. And so you would ask that if it's just a gravitational interaction, the only way to get the dark matter to be about the right amount is by fine-tuning the initial conditions. It's very unsatisfying. And so it's very nice. It's a very elegant idea that dark matter and standard model matter should somehow communicate, other than gravity. And so it makes sense to actually both list the possibilities for this and then try and find ways to constrain them. But it's certainly true that every limit this limit here is model dependent, and this limit here is model independent. Yeah. I don't think I fully understand your question, but I think I do have an answer. Say one more time. Oh yeah, they're just non-rotating, non-charged, and uniform mass black holes. So most of these limits probably wouldn't change if it's rotating. I don't think.
I was thinking that in rotation, you might have this kind of random stabilities that allow your.
We can talk after. I doubt that will work, but yeah. Physics can be much richer for sure. Let me tell you, because I don't want to run out of time. Okay, so one thing you might like to do with a WIMP particle is you can do a velocity expansion of its interaction cross section. Okay, so where x is 1 over x is v squared. Okay, I don't know why we use x. I should rewrite this to make it cleaner. Typically, in the classic WIMP, you assume that there is a velocity-independent piece, and this dominates the calculation. But sometimes we like to pretend that this piece is absent because if you have p wave, where you're velocity-dependent, this can actually change the limits from things like direct detection when you look for the particle. Because these particles are coming in with some velocity, and the velocity has tendencies to suppress, because velocity is 10 to the minus 3, v squared was 10 to the minus 6. And you can also think about cases where you actually go like v to the 4. The kind of scenarios that you find, like this is an S-wave cross-section is something like a fermion dark matter going to a fermion standard model particle via z prime. P-waves, something like 2 fermions have a T-channel annihilation to scalars, and D-wave is something like this, where a scalar dark matter goes to a fermionic standard model particle. One thing which is important, and I'll stress in a moment, is that when you have any of these processes, they often have, at tree level, you have a P-wave or a D-wave. At loop level, or a higher phase space order, you will often generate an S-wave piece, so a velocity-independent piece. So here, although 2 to 2 processes are D-wave, 2 to 3 processes are actually S-wave. And so if you calculate the, what is this? This is the S-wave, no, Yeah, the S wave cross section divided by the D wave cross section. Your suppression factors between the two are either maybe either 10 or maybe 100, or maybe 1,000. But this is important actually because it tells you you can't just switch up these. If you want to have P-wave dark matter, you can't just set this to 0 because generically it's regenerated at loop order. So if you actually take, yes, does that mean 5 minutes? That's good. I can do 5 minutes. If you actually redo the analysis and calculate what sort of profile you think you generate. So remember when I said you had a velocity independent profile, then it had a center plateau, and then it went up into this sort of in the density profile. The P wave and D wave, when you calculate this, give you something where you have some sort of initial rise and then it falls away. So the spikes that you get here are actually non-physical, and I'll explain shortly. But what this is really giving you is an annulus, right? So you core away the center. Instead of going to a flat density core, you core it to sort of nothing, and you get like an annulus of dark matter around your black hole. When this comes to calculating the limits, it's actually because you've taken away this central region, which is actually, a lot of where your dark matter was, your limits get a lot weaker. So if you have, this is your S wave limits I showed before, the P wave, I set the S wave peaks to exactly 0. My limits change by about, what's it, 1, 2, 3, is that two orders of magnitude, and the D wave case by 3 orders of magnitude. However, as I prefaced, you can't just set these to 0. So actually, the story behind this somewhat is someone scooped us to do this analysis, but they neglected the fact that this is a highly non-physical, actually look at this one. This is a highly non-physical scenario. And so the physics is actually somewhat more like this. So if I take, this is my 2 to 2 process, it's S wave, a 2 to 3 process is like 2 to 2 is P wave, 2 to 3 is S wave, so velocity independent, and you're only reduced by maybe a phase space factor, so like 8 pi down. So if I take that and I redo my analysis, and a couple of things which are interesting happen, the first thing which happens is that, I'm going to ignore this time, you lose this spike, this non-physical spike in your density profile, and actually what happens is your density profile goes up, and then it smooths out, and then it falls away, which looks much more reasonable. But also when you come to your density, when you come to the constraints, if I plot my F versus mass. So my S wave, where my velocity independent, let's look at the red line to say, my velocity independent constraints were down here at about 10 to the minus 9. My pure P wave, where I set the S wave to 0, was 3 order of magnitude, what was that? 2 order of magnitude less. Okay? But when you re-include the fact that there is a phase space suppressed S wave process, you actually only change the limits by maybe a factor of 2. The idea that you can gain by going to different velocity suppressions actually doesn't work, which is nice because it means in principle you can exclude and protect these things. Okay, the final thing I need to talk about is this the FIMP case. So recall in the FIMP case, what I'm doing is instead of starting in equilibrium and annihilating to get the final abundance of dark matter, I start with no dark matter and I produce dark matter, and then when that switches off, that's my final abundance. You find that, firstly, in a lot of cases, there are no limits. However, there's essentially sort of 2 different broad categories. It depends if the dark matter annihilates directly via an S wave to standard model, or if it annihilates via a T channel to maybe ZZ prime. So if this is I take this model where this is my dark matter, this is my standard model sector, and I have a connecting mediator. If I have this S wave process, it's difficult to get limits. I can do dark matter goes to 2Z primes, then it's much easier to get limits. In that case, you see the limits all exist. This is actually quite nice because these are sort of generic limits on freezing dark matter where generally there are none. But in this case, you see that depending on the mass of the Z prime and the couplings of T lambda, then I can exclude some part of parameter space. Maybe I only exclude something of order like, this is like 5%. But maybe, in some cases, this is competitive with microlensing bounds, even down to slightly lower masses. So this is the paper we're hoping comes out in the next couple of weeks. With that, I'm going to wrap up. So, dark matter is clearly a large problem for the standard model. It can't be explained within the standard model, and so we need to find ways to explain this. One possibility is to introduce new particles, and I talked about WIMPs and FIMPs in this talk. Another possibility is to introduce mechanisms that produce black holes which aren't linked to physics, being a quintessential example being primordial black holes of Hawking and Novikov Zeldovich. What's interesting is, if you have a population of both primordial black holes and particle dark matter, then you can get enhanced signals. And this seems to be tentatively hinted at in this overall experiment data, which is why I think it's interesting. More excitingly, many upcoming experiments are going to test all of these cases. There will be future experiments that look for dark matter. There are future experiments which are looking for primordial black holes. And because of this is a very nice area to be thinking about. In particular because a discovery of any signal in dark matter physics or primordial black holes will tell us a lot more about physics beyond the standard model. Finally, I spent a few moments talking about the tentative evidence of a new body in the solar system, and with my particularly favourite proposition that this could potentially be a black hole in our back garden, which would be a particularly exciting prospect. So, thank you for your attention, and yeah.